Good morning and good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Peter Ture from Business Review, and I'll be your host today. It is our pleasure to have with us Smith Interconnect, who will be presenting us on the webinar titled High Frequency Spring Probe Interposers for Space and Defense. Now, today's guest speakers with us will be Kevin DeFord, who is the Product Line Manager, Interposers and Backplanes. We also have with us today Dennis Murphy, who is the Key Account Manager for the, in this case, in terms of the actual connectors. Now, I'd like to welcome everyone here to On24. You notice that this platform is browser-based, so if you do disconnect for any reason whatsoever, please click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. That's the top right-hand box of your screen. So for you to submit questions, type in your question and click submit. We'll then allocate some time at the end of the session to address any thoughts or questions that you may have. Please also use the yellow help widget in case you need any assistance to move, resize and maximize any of the screens in front of you to help get a better view of today's session with Smith Interconnect. But for now, please allow me to hand you over to our first speaker of the day. Dennis, over to you.
Thank you, Peter, and thank you all for taking time out of your busy schedules today. So my name is Kevin DeFord. I am the Product Line Manager for Smith Interconnect. So I want to begin today by talking about the evolution of spring probe technology. So we'll talk about some basic terminology that we use when describing spring probes individually, and then we'll also talk about some construction methods as well. And then Dennis will approach the interposer construction methods and talk about some of the advantages that we can offer with interposers. So I want to quickly talk about the evolution of spring probes. So spring probes have been around for decades. It was first used in test fixtures for printed circuit board test, aptly called bed of nails. So that's the photo up here in the upper left. So some of you have probably seen these, but again, these have been around for about 30 years. So eventually we started to realize that spring probes had other applications. So down here in the lower left, this was a coax interface ring that was used in the ATE test industry. So this was essentially the perimeter of this ring here has probes and then coax lines in it to be able to interface between the motherboard and a daughter card in the ATE testers. So, and then eventually we started working spring probes into connector applications because of the fact that we could put them in very, very small spaces, as shown here in this cochlear application. And then eventually the spring probe interposer was born, which is shown here. So, and in around 2010, the spring probe interposers really started to become prevalent in defense and space application, and continue today. So. Now let's talk about spring probe and interposer applications. So spring probes have 3 or 4 major components. The first component is the plunger, which is typically made from hardened copper or steel and plated with electrolytic nickel and gold. The plunger makes electrical contact here between the barrel and the device under test. So a feature is added, it's right there. A feature is added to the tail of the plunger, which we call the bias cut, which guarantees that electrical contact is made between the plunger and the barrel. So the barrel is typically made from highly conductive copper and plated with nickel and gold, which completes the electrical connection between the plungers and the device under test and the PCB down below. So the barrel may have a retention feature shown here in number 2 to hold it into the insulator, or it may be free floating, which requires a two-piece design, which is used to encapsulate the probe, but allows it to float inside the insulator. The last component is the spring, typically made of stainless steel, but it can be made from many materials. Stainless steel is the preferred material due to its resistance to corrosion and high temperature life, up to 180 degrees Celsius. All of the components are designed and manufactured with high precision to ensure good electrical performance. Interposer probes can be designed with a variety of features depending on the application. We'll discuss a few of those designs, but keep in mind that there are many features that can be added to a spring probe depending on the application. So the first design here on the left, that's our bayonet probe. And it's a three-piece design. So the barrel can actually be pressed into an insulator, or it can be pressed into a receptacle, which allows us to extend the reach of the probe to greater than 1 inch. So imagine a receptacle with a spring probe on the top and a spring probe on the bottom that spans over that 1 inch. So the second design is it's a four-piece design, but it only has one moving plunger. So the solid plunger here is crimped into the barrel, and then you have a moving plunger on the bottom. So these can be designed to free float in the insulator, and the advantage here is that we can design this tip here, this solid contact, with different geometries and different lengths to span multiple heights. So the third design is our double-ended probe, and it has two moving plungers, as shown in the previous slide. The advantage here is that it allows more compliance between the top and the bottom device under test, or the PCBs, which allows for more tolerant stack, and it can be designed with both a floating design, or it can be designed with a retention feature to hold it into the insulator. So all of these design constructions have been tested in high vibration and shock environments and have passed rigorous test standards for both space and defense applications. So now I'd like to turn it over to Dennis to talk about some interposer design considerations. Over to you, Dennis.
Hi, all. I'm Dennis Murphy. I'm Key Account Manager and Sales Engineer here for Smiths Interconnect. Now that you've got some basic understanding of the spring probe construction, what do you do with them? How can you package it in a useful manner? The first thing I'll review is the retention of the spring probe itself within the housing. Housings are typically an engineered plastic of some sort. Tecapeaks and Ultims, they're just a few of our typical materials we gravitate towards. However, depending on the design requirements, both environmental or electrical performance needs, there's a whole bunch of other materials that we can consider using. So starting up here in the top left corner, you'll see what we refer to as the fixed barrel method, whereas the name sounds, the barrel does not move. Either from the retention devices, the retention features that Kevin illustrated in the previous slide, basically holding that barrel in place into the plastic housing. And then as the name implies, basically the compliance or the movement of the spring plunger interaction is now freely and independent of any other factors in the assembly, allowing both the top and the bottom plunger to move independently. Second bubble here, this is what we call the floating method. We designed the internal hole geometry to allow for us to capture the probe between the upper and the lower halves of the housing. This method allows for additional travel, oftentimes used in our lower profile solutions, where the probe itself does not have room for the larger internal compression due to the reduced overall height constraints that we're trying to achieve from the overall customer solution. If you guys have ever played with a child's toy that's kind of a bed of nails where you can put your hand in there and it presses the nails up and you can kind of see the impression, it's kind of like that if anyone remembers playing with those as a kid. Now we can move on to the housing design considerations. What we're showing over here on the left-hand side is really just a generic example illustrating several different features and layouts that can be incorporated into your interposer all in one. So this, like I said, it really is just more for visual purposes, so we can put it all in one common key place. The purpose of these solutions, or these features, allow for us to design with explicit focus to optimize for signal performance, or to fit specific space constraints within your system, or just increase the ease of installation or system reworkability, especially when we're utilizing our double-ended solderless probe approach, which is probably 95% of our solutions that we work with our customers on utilize the solderless approach. Some of the things that can be incorporated easily into the interposer design are the adoption of dowel pins, of bosses, anywhere to help with alignment purposes. We have the ability to incorporate additional through holes, hardware, things of that for securing or mounting the interposer into your design. We have the ability to create specialty cutouts to avoid, if you have other system level components already installed and you need to make sure that you've given your system enough room, and even add environmental or EMI gasketing if necessary. As Kevin will go through in more detail shortly, you can also tailor the patterns to allow you to pass different signal types. For example, single-ended RF signals can be passed through utilizing an individual signal probe centered around a grouping of other probes that are connecting as a ground shield. So if you look at this little image right here, we're showing that center pin that allows you to pass that's your actual signal pin. And then in this example, you're seeing that you've got 5 pins or 6 pins around. Those are what's creating your ground shield, essentially mimicking an RF single-ended solution. Additional ways that you can also pass RF signals, especially in a ganged array approach, would be to utilize what we refer to as a standalone coaxial, where a probe is pressed into a standalone dielectric and then inserted typically into a metallized or a grounded housing. In this image here is kind of what we're showing here. You can see we're taking this standalone dielectric single pin with a plastic housing, and then pressing multiple rows of those into another housing. And then you can see that we also have individual pins here standing or acting as the grounds that would act and ground the entire assembly itself. Again, we'll go through a little bit more of that here in a little bit later detail. Impedance matched differential pair signals can also be passed in a tight grid array, as seen here in the middle, as well as typical I/O, power signals, in pretty much any pattern imaginable. These arrays and patterns can range in heights from around 3 millimeters up to well over 25 millimeters when appropriate design considerations are taken into account. In typical pitches, we can get down to as small as 1 millimeter in some cases. Lastly, most designs start out as a machine solution for prototyping purposes, and depending on production volumes or design characteristics, molding can also come into play, especially if there is environmental sealing considerations that may be needed to take into account. So with that, this next slide is just going to be a quick animation to help better visualize some of the points I just spoke of. In this example, you can see that we're going to be showing a 2-piece housing that retains the probes. And there goes. I think it's coming. There we go. You'll notice that we're utilizing 2 different probes within the same housing. This allows us to provide a solution that can handle some high-speed differential pair signals along with standard I/O, while the larger probes that you're seeing on the other end are being utilized for high power. In this particular example, those larger power probes are about 8 amps per probe. All of this contained within the same connector. Next, all of this gets buttoned up with dowels and secured to the 2 halves, securing 2 halves.
Thank you, Dan.
Yeah,
I'll take it from here. Thank you. So, just a quick poll question for the audience. So if you would select one or the multiple choice. So what is your largest priority in board-to-board and mezzanine applications? Is it high-speed, small footprint? I'm sorry, I said speed. High-density, small footprint? High-speed digital? So differential signals? Or is it RF performance? Or is it one or both of these things? So if you would take a moment to answer this question. We'll display the results shortly.
Thank you very much for that. Thank you for that, Kevin. What you could say, so then what motivated you to address the audience with this poll question? All right. Let's see. Okay. All right. Let's go on to the results and see how the poll is doing. So as you can see, Kevin, A or B or A and C are the most popular answer. Any thoughts to that?
Well, thank you, Peter, and thank you for your input. It really doesn't matter if we're talking about high-speed digital or RF when it comes to bandwidth and performance. So good design really dictates both criteria, and it starts with our simulation. So I'm going to talk about a few cases in RF and digital design in the coming slides. Sorry, I forgot to advance the slide there. And I'll present some RF examples and then a digital example as well. First, I want to talk about simulation. So, before we get into the RF and digital performance, it's important to qualify the results that we're presenting here. So most of the data that you're going to see from this point forward is going to be based on a simulation. So it's important to have confidence in your simulation results because every case in a design cannot be tested without, large investments in test collaterals and time. So, as engineers, we have to make decisions up front, and so simulation is the way that we achieve our confidence in our design. Simulations are only as good as the data that we put into the model, and they must be correlated with measurements, which is what we're showing on this slide. So the RF results presented here. So Dennis spoke about the I don't know if he mentioned Gatling, but this is the Gatling style connector or interposer that we use. So it's a signal pin with 4 pins, 5 pins. It could have up to 8 pins, depending on the amount of shielding we need in the design. The center pin represents the signal pin, and the pins on the outer periphery represent your ground pins or your return pins for the signal. So as we're showing here in the insertion and return loss plots, the blue line is the simulated result, and the red line is the measured result, which is also, it's a de-embedded result. But you can see, it may be very difficult to see, but this is actually through 67 gigahertz. You can see that we cross the minus 1 dB point at about 60 gigahertz. And then for return loss, in the measurement data, it's about 25 to 30 gigahertz that it passes minus 20 dB point. And it's better than 10 dB through the full bandwidth of the measurement. It's also important to note here that the length of this interconnect is a little over 1/4 of an inch in length. So the differences between the results, between the simulated and the measured results, really has to do with real world effects of measurement and how we launch signals into the interconnects. Now this is an RF example, a simulated result. So again, a Gatling style connector was simulated. In this particular case, we have a center signal pin surrounded by 5 return pins. So the results for insertion and return loss show better than minus 1 dB or at 40 gigahertz, and greater than minus 20 dB at 25 gigahertz. And the impedance in this case is 52 ohms. Now, so, why not 50 ohms? In some cases, when you interface with printed circuit boards and the device under test, the PCB pads and the vias can influence the actual signal path. So it may not be optimum in every case to design for 50 ohms or 100 ohms if we're talking differential. You may want to design with a slightly higher impedance or lower impedance to offset some of the effects of printed circuit boards and the device under test or other printed circuit boards. So in the next example, this is a differential array. So we have two signal pins surrounded by ground pins. This is what we call, for simulation, a 10A pattern. So it's 10 pins. The two pins in the center represent the signal, and the outer pins represent the returns. In this particular case, the board height was 130. Using the 101267 probe, which is the probe that was shown on the previous slide, that has a board-to-board height of 0.13 inches, or a little over 3 millimeters. So in this particular simulation, we added 12 inches of trace on both ends. On the top board, there was 12 inches of trace, and on the bottom board, so to include a total of 24 inches of trace, and then the vias as well in this particular example. So you can see in the top graph here, what we're showing here is the simulated result for the connector itself, which shows almost negative 30 dB of attenuation through 50 gigahertz. So that's important because the connector itself again has better than minus 1 dB through 40-50 gigahertz of performance, but in a real-world application, we're actually looking at minus 30 dB when you include the trace and the vias into the stack. So then we take that information and we plug it into a SPICE simulation to produce the eye diagram shown below. In this particular case, we simulated 25 gigabits per second. The rise time for this particular simulation was 10.25 picoseconds, and the unit interval was 40 picoseconds. So now let me turn the presentation back to Dennis so he can talk about some interposer construction and features. Over to you, Dennis. Dennis?
Hello, Dennis.
Yep.
Are
Sorry,
you available?
Guys, yep, I'm back. Sorry, I had a technical difficulty there. Sorry about that. So now we're looking at some of the advantages of integrating a spring probe connector or an interposer into your system level designs. Going through some of the key points we are showing here, you'll see us mention the ability for low profile to high compliance ratio, also referred to as our travel. Typically, a 4-to-1 height to available travel is standard. The ability to survive and operate through harsh shock and drive environments. When we approach a new design with a customer, it's important for us to understand the details of what the survivable versus the operational needs are from the start to allow us to make sure we provide a probe design and a housing method appropriate for your individual needs. The values here are just a general example of some of our capabilities and completed designs that far exceed these parameters, albeit on a case-by-case basis, is what we've been able to accomplish with other customers. Typical resistance of many of the spring probe designs fall in the 30 to 50 milliohm range. Moving on down, cycle life. What we find with cycle life concerns is that it is not typically a factor that is deemed critical, as most of the applications are designed and intended to be installed maybe just a handful of times and then stay mated for life. Threading or micro movement over the life of an installed state, however, is often the question that comes up more often. By the nature of using a spring probe, this concern has all been eliminated as far as spring relaxation goes over time. These solutions are intended that they can be mated in a compressed state for years with minimal relaxation over time, ensuring good signal contact while also exposed to shock and vibe environments. By far, the most common application and purpose we design for is the solderless interface, as I've mentioned. And by that, we are typically using a double-ended spring probe where the customer's board application would basically have target pads on both boards, and the act of compressing the interposer between the boards and being held mechanically to maintain that compression ensures the signal pass freely. This offers many benefits. It prevents any FOD from interacting with the interposer because it is an installed state now after the washing and the cleaning of the boards. It allows for the system to be in a mated or demated for rework and testing freely without risk of damage to solder joints during the unmating processes. It can save on installation costs by not actually having to be soldered to the boards. Not to mention now you're only using one interposer or connector instead of two mating halves. Lastly, the added benefits of an interposer solution is the tolerance stack-up absorption that they can provide over other interconnect options. As you'll see here on the left, you can see where we're showing or illustrating the different degrees of freedom that are allowable. X and Y will change based on the chosen pitch versus the pad size being used in the design. Z is determined by the amount of travel a particular solution may be designed to have. And then you also have the added angular and rotational misalignment capabilities an interposer can provide. Again, as to how much will vary greatly by design. All right, so we've got another poll question for everyone. When you're looking at approaching a new board-to-board connection, what do you feel are your most challenging constraints? Limitation in stack height options, axial misalignment between your boards, general tolerance stack-ups, in particular meaning more like the Z travel stack-up, or the mating forces. Give you guys a couple of seconds to click on that. Okay. Guess we can move on.
All right, so let's check to see what the results are now. So as you can see, stack height constraints is the most common answer. Any thoughts on that?
Which I would say this, for the most part, aligns up pretty well. In most of our applications with most of our customers, stack height constraints meaning that you're really trying to find a custom height. You know, if you're using the COTS products that are out there on the market, you're kind of already painted into the corner of, you know, you have option A, B, or C, and that's it. Which is again, another great reason why Spring Probe Interposer is such an attractive solution for many customers, is because we have the ability to basically tailor the Spring Probe to meet exactly whatever your stack height constraint needs are from a physical compressed state dimension. But also, I would say the tolerance stack up, basically having the ability to where, you know, if there is variances in your board thicknesses or other system constraints, having that Z travel variable there is really probably, I would say that aligns pretty well with what we see as the top two with our customer base. So thanks for that input, everyone. So now what I'll do is I'll run through a couple of examples here of some, you know, what some typical interposer solutions may look like, as well as some of the benefits, and just, again, trying to illustrate and provide you all some ideas of how they can be utilized, allow you guys to kind of think outside the box with some of these a little bit. So this first one here, we're showing how you can customize the layout of a pin array to meet your specific profiles you may have to maximize your available space in your system. Whereas, you know, typical COTS connector is going to be typical, 4 by 80 contacts, rectangular. With spring probe interposers and the way that we utilize them, you're basically allowed to develop or design any sort of feature that you need. So, for instance, if you're using a circular board, you can make a connector that will match the profile or the outside diameter of that actual board. Here, we're also illustrating some of the mechanical features that can be incorporated to aid in the aligning the interposer to the board or the mating boards. You can utilize alignment features such as an extended length dowels that would be able to aid in the alignment of the next level interposers in your next level of the stack. This approach can be very useful for assembly reasons when dealing with multiple small boards stacks in the system. This is also a good example to further illustrate the solderless interface, as you can see here from the small gaps between each one of the board interconnects. And also, I want to illustrate or accentuate that an interposer solution can be designed that the actual housing of the interposer itself can be the hard stop between your boards, essentially meaning that these probes can be fully compressed all the way to the full surface of the plastic housing that we designed them for. Or you can take an alternative approach where basically we incorporate features into the housing itself that allow for hardware that you can basically mount the connector specifically to one of the boards, being fully compressed to that board, and then leaving a gap in between your next board, and the connector itself. This thus allowing for that Z-tolerant stack up or the probe itself to travel, to move, again, allowing for taking up variations in board thicknesses or other manufacturing tolerances in your next level assembly. This next example here is kind of a cool one that we've done before. While still a similar situation as previous slide accomplishes things a little bit in a different manner. In this solution, if you kind of think of the bottom board, PCB-A, as a motherboard, and this is a single connector solution that allows you to get signals off from board A all the way directly to board B here in the center section of the connector, or also going from board A all the way to board C on the outside wings of the connector. And you accomplish this, but it does require you to have basically a hole in the board that matches the geometry or the feature of the connector. But again, you'll notice it's going to allow you to incorporate that solderless interface to provide you the degrees of freedom in the alignment, the X, Y, and Z directions, and ability to easily dismantle the assembly if needed for rework, test, or repair. Lastly, you'll notice that we are providing a specialized mounting method that allows for the tolerance absorption between all three representative PCBs by keeping the interposer independently mounted from the PCBs. Finally, this last slide is an example where we were required to match an existing envelope for a system that was already fielded and was having signal intermittency issues due to the shock and vibe environments that the system generates. Working side by side with the customer and Smith engineering teams, we were able to provide 3 different interposer solutions used to replace the existing solution with minimal changes on the customer's end. The interesting thing about this was that because we had 3 different interposers to design, we made a point to utilize common components between all 3 for an increased economies of scale at production volumes to help in our ability to provide a cost-competitive solution long-term to support the program. The solution had Smith replacing the competing bent metal style technology, contact technology that exhibits the known metal memory problems that will come from being in a mated condition for long extended periods of time, which was the root cause of the customer's issue. Again, utilizing the actual coil spring eliminates the concerns of extended life in a compressed state and dropping signals during the environmental exposures. So with that, we'll swing back things over to Kevin to wrap up.
Thanks, Dennis. So, in summary, we introduced 3 spring probe designs and showed some different methods of construction for interposers. We gave a few examples, how interposers can be designed into RF and digital applications. And we discussed the importance of simulation confidence. In the simulation example, we demonstrated that we had good measurement correlation to the simulation and performance well beyond 40 gigahertz. So Dennis, he explains many of the examples of how interposers can be implemented in the applications and the advantages that interposers bring, such as low profile, high reliability, high density, and high cycle life, especially in applications that are prone to fretting. And so interposers can be used in high frequency applications and limitless applications. So in this presentation, we've really only scratched the surface of the possibilities of spring probe interposers. So if you have further questions, I ask that you contact one of our sales engineers in your region, or you can please leave your details in the Q&A section, and we can have somebody contact you. So with the limited time that we have left, Dennis and I can try to answer any of your immediate questions.
Yes, thank you very much for that, both Kevin and Dennis. Just a quick reminder to the audience, for you to ask questions, type them into the box at the top right-hand corner of your screen and click submit. But in the meantime, the first question is, so Kevin and Dennis, do you offer ingress protection or EMI shielding in your interposers?
That's a good question, and the answer is yes. We offer both ingress protection and EMI shielding. So ingress protection, we offer gasketed solutions that can pass, ingress up to IP67, possibly even higher, depending on how we construct the interposer. And typically for EMI shielding, what we do is the Gatlin style connector that we introduced, which is pins that are inserted in a circular array or a rectangular array and put into plastic. You can have press features on those inserts to press them into metal housing that can provide EMI shielding. And then we can also incorporate EMI gaskets into the connector design or interposer design.
All right, thank you very much for that. The next question is, you mentioned shock and vibration. What levels have you tested interposers to?
Okay. Yeah, so, it just really depends on the application. For vibration, your typical 20 Gs, 10 hertz to 2,000 hertz. We've tested multiple designs in those environments and have no issues with, any intermittencies or anything like that. So in shock applications, I think of two scenarios that one's more recent than the other, but we just tested an application where we had to withstand 300 G shock and be operational. So in other words, passing signals during that 300 G shock. And in that particular case, we were monitoring bit error rate at 300 Gs at 5 gigabits per second and passed without any bit errors. Excuse me. Another application I can think of is an application where we had an SRS shock. It didn't have to be operational during the shock, but it had to be functional before and after that shock. And in that particular case, it was 2,200 Gs that it passed as well. So.
Well, thank you very much. Dennis, do you have any input also to add on to that?
No, I think Kevin covered that one pretty well.
Sure, no worries. So another person asked, what are typical development lead times and what is your development process?
Yeah. So a typical interposer design is, it kind of starts off with an engagement with the sales engineering team, and you all as the customers or your engineering teams. The process can be as quick as a week, or it can be several months. It really, really does depend on the complexity of the design, what you guys are wanting to achieve, as well as how mature the design actually is. So from a design development standpoint, we would have that initial engagement, that initial kickoff with your teams and us. We'd start working on the development side, again, a couple weeks, and then we could then be in the position to where design finalization could be a week or two after that, and then we could get the quoting process started. So all in all, from the time of engagement to the time of ready to accept POs can potentially be as short as 3 to 4 weeks. It all just really depends on the complexity of the design, and then obviously it could go much further than that. But then as far as delivery and lead times go, that really is a wide open answer. It really does depend on what the programs or what the probe design actually is and things there. So there's not really a good solid answer on that regards.
Mm-hmm. Sure, thanks for that, Dennis. Kevin, do you have anything else to add on to that?
No, I think Dennis covered that.
Okay, sure. So one person asked, in terms of loss, how does a spring probe RF connection compare to other blind mate solutions like SMPs?
So yeah, I mean, we've designed out a lot of connector applications that utilize things like bullets and SMPs. So the interconnects themselves, the interposers, can operate. I've seen applications well into the 56 gigabit range in terms of RF. Anything above 50 gigahertz, we should be able to achieve. The Gatlin style connectors have been used and utilized in many of those types of applications, and where they've actually replaced those types of technologies, the bullet technology and the SMPs.
Fine, thanks for that. So another person asks, with soldered in pogo pins, how best to handle assembly cleaning if clean-free solder is not allowed?
You want to take that one, Dennis, or should I?
I'm going to say if you want to take that one, Kevin.
So, just like, any connector, if you're going to solder the connector onto a PCB, it's best to cap off the connector itself. So I would recommend protecting the electrical portion of the interposer during any kind of cleaning. The biggest problem with any kind of connector is if you get cleaning solutions, fluxes, and other contaminants down inside the connector, they can affect the operation of the connector and the lifespan of the connector. So generally, that's why the solderless approach is the most popular for us, to avoid contaminating the connector and to allow for ease of rework and ease of maintenance in the field. So yeah. So the best way to handle it would be to cap it off securely, so that you don't allow ingress of contamination into the connector.
Mm-hmm. Great, thank you for that. Dennis, do you have anything to add on to that before we conclude?
Nope, I don't.
Okay, so thank you very much to the audience. And just a quick reminder, if you did not get your question answered or you have any further questions, please send them through and they'll be answered at a later date. So that leaves me to thank both Kevin and Dennis for a great presentation, and to Smiths Interconnect for sponsoring this event. Now, to all the attendees, you will receive an email shortly on how you can access the on-demand version, or you can access it at our website, www.business-review-webinars.com. We look forward to sharing future webinars with you, so please do keep an eye out on our website as mentioned, and follow us on Twitter at BRWebinars for daily updates and join our LinkedIn community group. Once again, thank you all very much for attending today's session with Smith's Interconnect, and hope you will have a very great day. Thank you for attending.
Thanks a lot, all.
Thank you all.
Thank you.